Hello, viewers. Good morning. Check out this shirt I got in Rome. Pretty cool shirt, huh? Oh, you have the Life as a Joke version? I saw the Life as a Joke version in Florence, and I thought, man, I really love that shirt. And then when I got to Rome, they didn't have the version with Life as a Joke. And dang. Because that's the one I originally, the one I really wanted was the one that said Life is a Joke. But this is the only shirt I have where walking around you can see people reacting to it. Do people react to you and you wear this shirt? Okay. So I'm going to go ahead and get started. This is SL 1015. Okay. So we finished talking about momentum, or sorry, about energy last time with our discussion of work. And today's lesson is going to be about something called momentum, which is kind of similar to energy. So momentum, okay, so it's a new topic. All right. Momentum is denoted by P, okay, and the so P is for momentum. P is also for power, which we learned about last time. Typically, momentum is a lowercase p and power is an uppercase p. But you know, if you need to distinguish between the two, you always can. You can put a subscript or whatever. The formula for momentum is mass times velocity. So we can see that it's sort of similar to kinetic energy in the sense that it depends on your mass and your speed. Okay. However, one really important difference is that momentum is a vector. Okay. And the thing about vectors is that it has a direction. So you might remember kinetic energy is 1/2 mv squared. Okay, kinetic energy is 1/2 mv squared. So if you have a negative velocity, like for example, if your velocity was -5, that negative gets squared and becomes a positive. So your kinetic energy is the same whether you're going to the left or to the right. However, if you're going to the left, because there's no square here, your momentum is going to be negative. Okay? So that is important. That's a crucial difference. What are the units of momentum? Well, momentum is a mass times a velocity. Okay? Momentum is mass times velocity. So mass is kilograms, and velocity is meters per second. So kilogram meters per second are the units of momentum. All right? Let me give you a really easy mnemonic so that you can remember the formula for momentum. A nice way to remember the formula for momentum, I'll box this in by the way, is to think about it not as P equals mv, but mv equals P. And then you have MVP. Who knows what MVP stands for? Type it in the chat if you know what MVP stands for. No, it doesn't stand for most valuable player. It stands for most valuable physicist. And that's you guys, all of you guys. You're the most valuable physicists to me. Okay. I say that joke every year, and every year students just walk right into it. I love it. Okay. So okay. If you have this is the momentum of basically a single particle. Okay. It's the momentum of a single particle. If you have multiple things moving around, for example, you know, the solar system has different planets that all have different velocities and different masses, then the total momentum is simply the sum of the individual momenta. Okay, so we add them together. Now here's the cool thing about momentum. All right. Now I would say what makes something cool in physics? Something is cool in physics if it makes your life easier, if it makes it easier to solve problems. So momentum is a tool that allows you to solve problems more quickly, more easily. Just like energy is cool because it lets you find the velocity of a roller coaster at the bottom of a ramp without worrying about the shape of the roller coaster track. Okay? That's cool. Momentum is the same way. So the cool thing about momentum is that the total momentum is conserved, okay, The total momentum is conserved in collisions. Okay, so whenever two things are hitting each other, like bouncing off of each other, you can be guaranteed that momentum is going to be an important tool in analyzing that problem, okay? Anytime things are bouncing off of each other, all right? I feel like I'm flipping someone off in some other culture, like if I go like that. Same thing with energy. The term conservation in physics has a very specific meaning. It means that the total value is not changing as time goes on. So that total momentum initially is going to be equal. So this is the total momentum before the collision is going to be equal to the total momentum after the collision. Okay? So this is called the law of conservation of momentum. Okay? That's the law of conservation of momentum. So really, this is going to be a fairly short lesson today. We're just going to do a couple of examples of applying the law of conservation of momentum. So there's a couple of problems that you're very likely to see. Okay, and so we're going to go over how to solve these types of problems. First type of problem. I'm going to call this a recoil velocity problem. Okay. Let's suppose that we have an astronaut with some kind of a projectile launcher, so maybe a rocket launcher, okay? So astronaut plus rocket launcher okay? Astronaut plus rocket launcher have mass, let's say 70 kilograms. Rocket, actually, can I just say rifle? I'm just going to say rifle. The reason I said rocket launcher is I wasn't sure if rifles would work in outer space. Let's suppose you have a rifle that works in outer space, okay? So astronaut and rifle have a mass of 70 kilograms. The bullet has mass, let's say 0.015 kilograms. Okay? Now, astronaut starts at rest. Okay. Do this. And shoots the bullet to the right. And we'll say the muzzle velocity of this bullet is 600 meters per second. Okay? What is the recoil velocity of the astronaut? That's a question. Okay, so let's draw a picture of this. So we start out with the astronaut like this. Here's the rifle. Like that. And so this is before. And then after, the astronaut shoots the bullet and they recoil. So they recoil backwards, and the bullet right here goes forward. Okay? So we're going to use conservation of momentum. So we have total initial momentum equals total final momentum. Now, before, notice how I said that everything starts at rest. Okay? And because the formula for momentum is mass times velocity, if something is at rest, then it has no momentum. So the initial momentum of this astronaut rifle bullet system is 0. Okay? Now let's look at the final momentum. So the final momentum is still going to be 0, but it's going to be made up out of two parts that are not 0. Okay? So first, we have the momentum of the bullet. The bullet has a mass of 0.015, and it has a velocity of 600 meters per second. So this is the term for the total momentum that comes from the bullet. We also have the momentum of the recoiling astronaut and rifle, which I said has a mass of 70 kilograms. And it has a certain unknown final velocity. Okay? Has a certain unknown final velocity. So, we can solve this equation for the final velocity. I'm not going to show the math because I'm running out of space here, but I will write down the answer. So 0.015 times 600 over 70. So the recoil velocity of the astronaut is going to be minus 0.13 meters per second. Okay? Now, in general, the way it works is when two things get pushed apart, the heavier one is going to go a lot slower. Okay? So the astronaut is much heavier than the bullet, has a lot more mass than the bullet. And so consequently, the astronaut has a much smaller recoil velocity. The other thing you want to notice is there's a minus sign here because the recoil velocity is in the opposite direction from the way that the bullet was fired. Okay? So you might ask the question, well, why do I have this happening in outer space? Because when you are firing a rifle, which I've never actually done, I don't even think I've ever touched a rifle before, but if you are firing a rifle on Earth, okay, you fire the bullet, okay, and you recoil, but that recoil is absorbed by the Earth. So you don't actually go flying backwards, okay? You don't go anywhere. And the reason for that is because the Earth has absorbed that momentum, not really you, okay? So that's why I tend to have momentum problems set in outer space so that we can really see what is happening to the things afterwards, okay? When you fire a bullet on Earth, your body and the Earth absorb the recoil. And because the Earth is so massive, there's hardly any recoil at all. There is a recoil, but it's a recoil that is incredibly, incredibly, incredibly slow because the bullet is so much lighter than the Earth. Okay. So I call that a recoil velocity problem. Okay. So let's do another example. And I'm going to call this a completely inelastic collision. Okay, so a completely inelastic collision means that the things colliding stick together. Okay, so it's like, you know, something like they stick together afterwards. Okay, so let's do a problem here. We have two astronaut lovers. Okay, these are two astronaut lovers. Float towards each other. The two astronaut lovers float towards each other. They collide and hold on to each other. Okay. What is the final velocity of the pair? Now I haven't given you any data yet, so I'm just going to draw the necessary information into the picture. So we have this astronaut. And we have this astronaut. We'll draw their visors. Okay. And this astronaut has a mass of, let's say, 70 kilograms. And this astronaut has a mass of 50 kilograms. Okay. This astronaut is headed to the right at 10 meters per second. This astronaut is headed to the left at 4 meters per second. Okay. So, and then I'll draw some hearts here. I'm only going to draw 2 hearts for this person. Oh, actually, I'm going to draw 4 hearts for this person. My bad. Okay, we can see that this astronaut has a much greater velocity, so this astronaut is kind of like more desperate. Okay, and because that astronaut is more desperate than the other one, that's going to create a rift between them, and I don't think it's going to work out between these two astronauts. Okay, afterwards they collide and they hold on to each other. And they can't kiss each other because their visors are down. It's outer space, so they couldn't do that without connecting their helmets. Okay. So we want to figure out what is the final velocity. And so we are going to use the conservation of momentum. Initial momentum equals final momentum. So the initial momentum has two parts. We have the momentum of the left astronaut and we have the momentum of the right astronaut. And the formula for momentum is mv. And so the mass of the left astronaut is 70 and the velocity is 10 meters per second to the right. So that means that the initial momentum of this one is 70 times 10. Then we have to include the mass of the 50 kilogram astronaut. Okay. Which is 4 meters per second to the left. So the second astronaut has a momentum of 50 times -4. So the initial momentum is 700 minus 200, 500 kilogram meters per second. Afterwards, the two astronauts collide and stick together. So if two things are stuck together, that means that they have the same velocity. If they have different velocities, then they would be drifting apart. Okay? So to be stuck together means that they have the same velocity. All right? So my final momentum is going to be, 70 V final plus 50 V final. Okay? They both have the same final velocity. It's not V final 1 and V final 2. Okay? So because they have the same final velocity, we can collect like terms. All right? Collect like terms. So 70V plus 50V is 120V. Divide both sides by 120. And I get 4.2 meters per second is the final velocity of the pair. All right. Normally, I will not. Normally, I'm not going to write these as two separate terms. Okay. So when two things collide, you can basically treat them as a single object that has the combined mass. So in future problems where we have two things that are stuck together, I would just skip immediately to this part. Okay. Notice how the final velocity is positive. Why is that? That's because the rightward momentum was greater than the leftward momentum. Okay. If the leftward momentum had been greater than the rightward momentum, then once they collided, they would be drifting to the left. Okay? So I think about this a lot in the context of, like, say, football. Okay? If two people collide in football, which way are they going to go? All right? So why am I at a disadvantage in football? It's because if I'm up against someone who weighs twice as much as me, then in order for me to have the same momentum as them, I would have to be going twice as fast as them to have the same momentum. Does that make sense? They have double the mass, so I have to have double the velocity in order for us to collide and be at a standstill. Okay? So that makes momentum. That's something I think about. If someone is 3 times the mass of you, then you have to have 3 times the velocity as them to overcome them in a collision. So this is maybe part of the reason why SUVs are a thing. So sometimes, especially parents are like, "Oh, we want you to have an SUV so you won't get hurt in a collision," and the reason why is because an SUV is going to be just continue forward in a collision if it's with a car that is lighter than it. Okay. The third example I would like to do, I'm just going to call it a general problem. Okay. So just for this general problem, we have a before the collision and we have an after the collision. Now, before the collision, we have, I'm just going to have this be with blocks. Okay. We have a 3 kilogram block that is headed this way at 5 meters per second. Okay. And then we have a 1 kilogram block that is headed this way at only 2 meters per second. Okay, so what's going to happen is the 3 kilogram block is going to overtake the 1 kilogram block and sort of bump it from behind. Okay, so it comes over and it bumps it from behind. And so as you can imagine, the 1 kilogram block is going to speed up and the 3 kilogram block is going to slow down as a result of that. Okay. So the 1 kilogram block is now headed to the right at, let's say, 4 meters per second. And then we want to know what is the final velocity of the 3 kilogram object. Okay? So the initial momentum is going to be m times v, so 3 times 5, 15, plus m times v, so 1 times 2, 2. So the initial momentum is 17 kilogram meters per second. All right. The final momentum is going to be the 3 kilogram mass has an unknown velocity, so we're just going to write its momentum as 3v final, mv. And the other one has a momentum of 1 kilogram going to the right at 4 meters per second, so that's 1 times 4, 4 kilogram meters per second. Okay? So this is an expression for the final momentum. Now momentum is conserved, and therefore these two are equal to each other. So 17 equals 3v final plus 4. Subtract the 4 to the other side. We have 13 equals 3v final. And then divide both sides by 3. And we get that v final equals 4.3 meters per second. So it's as I said, as a result of the collision, the 1 kilogram sped up and the 3 kilogram one slowed down. All right. One thing I want to say is that momentum is also conserved if you have collisions of 3 things simultaneously or 4 things or however many things are colliding simultaneously. Momentum is still going to be conserved. Generally speaking, though, usually you just do a collision of two things, and the reason is that it's in nature, it's a lot less likely for 3 things or more to be in the same location at the same time than it is for 2 things to be at the same location at the same time, right? If you think about it, going to the grocery store, you're fairly likely to see someone you know at the grocery store. You're less likely to see 2 people you know all arriving at the same time, okay? So for that reason, you know, a lot of the times we'll just be doing collisions with two things. All right, so that's my lesson for today. And so I will see you in the Zoom room in just a moment.